decomposing fluid flows according to their dynamics, a tutorial on dynamic mode decomposition of fluids data. And this is a presentation that's going to be given by two speakers. Our first speaker will be Maziar Hemati, and he will then be followed by Matt Williams. And just some quick information about our speakers. So Maziar received his PhD from UCLA. He then went on and did a postdoc at Princeton, and is now on the faculty at the Aerospace and Mechanics Department at the University of Minnesota. Matt Williams received his PhD from the University of Washington and then did a postdoc at Princeton. You're going to notice the theme here as we go on in this session. And is currently a researcher at the United Technologies Research Center. So with that, we'll turn it over to Maziar.
Thank you, Doug. So I'm Maziar Hemati, University of Minnesota, and I'm going to be giving this talk with Matt Williams, who's at UTRC. I'm going to be talking about dynamic mode decomposition for the analysis of fluid flows. Dynamic mode decomposition we're going to be calling DMD. You've seen that acronym already. And before we dive into DMD, we're going to take a step back for a second. I want you to just take a simple message from art. Okay, so we're going to look at this set of lithographs by Pablo Picasso. Okay, and this is kind of the general theme I want you to keep in mind as we think about dynamic mode decomposition, but also these modal decompositions in general. Okay, so Pablo Picasso, over the course of 2 years, put together this series of lithographs, again, collectively called Bull. And the basic question he was asking is, what makes the essence of a bull? What is a bull? Okay, and so to address this question, over the course of these 2 years, he began taking details away from the bull. Okay, until he arrived at this final stick figure. Well, we might call it stick figure, but I think all of us in this room, we look at this, we could recognize that as a bull to some extent. If you disagree with me, then at least somewhere during this process, one of those tiles you could see, that is a bull, that is the essence of a bull. So that's really what we're going to try to do with dynamic mode decomposition, but we're going to be decomposing the flow in terms of its dynamics. We're going to be destructing all of these snapshots, this complexity, into a stick figure. And basically the question of where we stop really is going to depend on the question that we're asking. Okay? So this is kind of the general idea that we're after. And so what does DMD really do? So as I said, we take a sequence of snapshots. So think of this as just a video. Here it's a time series of vorticity. And we feed that to the DMD algorithm, and out comes something that we're going to interpret as a cartoon of that fluid flow. Okay, so DMD gives us a set of spatial structures, and it gives us simple dynamics associated with those spatial structures. So it gives us frequencies and growth and decay rates associated with these spatial modes. Okay. And so we can use these spatial structures and their associated dynamics, again, to reconstruct that fluid flow in terms of a stick figure or a cartoon. And what that cartoon will allow us to do is, first we can describe the flow by looking at the spatial structures and their associated temporal frequencies. But also, if we have that cartoon, we can use that for in a predictive capacity. So we can have a model that predicts into the future, so we can design control algorithms around this. We can use it for sensing, we can use it for optimization, and things of that nature. Okay. So let's take a look at how is DMD different from maybe POD. So we have this sequence of snapshots. So this is just flow over a cylinder, contours of vorticity. And the POD perspective, which you've seen already, is to take that video, look at all of the frames of that video. Those are the snapshots. I'm just going to look at it as a collection of snapshots. Okay, and then we heard you look at correlations between different areas of space, and places with high variance are associated with highly active regions and dynamics and things of that nature. What DMD does differently now, rather than just looking at it as a collection of snapshots, we look at it as a collection of snapshots that are related to one another by dynamics. There's an underlying dynamical system that governs the evolution of this, and we're going to represent that as a linear map. So let's represent each snapshot as a vector x, okay, with the subscript denoting a time step. So x0 is our initial snapshot, x1 is the next one, and we can relate x1 to the initial one through this map A. So this is just the n by n matrix A. So we take A times x0 gives us x1. And I can apply A again from x1 to get to x2 and so forth till I complete that video sequence. And so you can really just take that as a relationship of A to the kth power times x0 to get snapshot at time step k. Right? So this is how we can use DMD in a predictive capacity. And Matt will take off to talk about why prediction may not be enough.
Thanks. Yeah, so as Mazi said, one way of using DMD is for prediction. That's generally the goal of time series analysis, right? You give me something changing in time, and I want to predict what's going to happen. But I think one nice benefit of DMD is why it's in this session, in that it lets you pick out more qualitative features. So what kind of spatial profiles do I expect to see, and what are their behaviors going to be? Are they going to oscillate? Are they going to grow? Are they going to decay? Things like that. Things that give us some insight into what's happening in this representation. So the main idea behind DMD, as we said before, is that there's some operator A, there's some matrix A that's governing how this system evolves. And since we care about these longer term features, what we want to do is decompose A using an eigen decomposition. So basically we're going to split it up into three matrices, V, lambda, and V inverse. V is a matrix of eigenvectors, so each column of V is an eigenvector of A. Lambda is a diagonal matrix of eigenvalues, ordered in the same way we ordered the eigenvectors. And this, V inverse is there, so it's a similarity transform, so that these two are in fact equal, right? And this is linear algebra, but the basic idea of why this eigen decomposition is the right thing to do for the features we care about is that, if I want to predict xk, given x naught, as Mazi said, I multiply by a to the k. But the idea is with this eigen decomposition, what I can do is write xk as this matrix vector product, I guess, where V is basically holding the spatial profiles. And these three terms here are telling us how much each eigenvector contributes. So this alpha term, which we're defining as V inverse x naught, is basically how much does it contribute at time 0? And lambda to the k is basically telling us, all right, how does that contribution change in time? Which modes become less important, which modes become more important, and which modes basically just oscillate, right? And this is pretty much linear algebra. Just to make it clear, I guess, why this is a modal decomposition as opposed to something else, if we took this product and wrote it out, we could write it as a linear superposition of the eigenvectors, which are going to be spatial modes, the alphas, which are going to be, again, the coefficient at the initial time, and the lambdas, which capture time dynamics. So basically, V is a mode, a DMD mode. Lambda is a DMD eigenvalue, which tells you how temporal dynamics appear. And alpha is the relative contribution. So who matters when? Okay, just to make it more concrete, if you gave me a snapshot xk, then we'd write it as a superposition here, where each of these profiles is the corresponding mode multiplied by its coefficient. And if we let k change, if we let time evolve, then effectively what we see is a movie where you have the flow here, which has multiple frequencies, but it's written as a sum of many modes, each of them which only have one frequency. So in this case, these are all oscillating at different frequencies. Okay. Now, all of this has been assuming I know this matrix A, and I'm going to give you these modes, and we're going to reconstruct this profile. And in fact, that's exactly the opposite. It's the backwards of how you normally use DMD. The game is really, you give me this movie, and my job is to tell you what these modes are and what that matrix A is. So now what I'm going to tell you about is the DMD algorithm, which is meant to accomplish that. All right. So DMD can be applied to really any time series. Just to kind of ground things, we're going to assume, again, this flow over cylinder example, where the assumptions we're making are that this is two-dimensional, so each snapshot is a matrix. But you could apply this to any type of data. It could be a tensor, whatever you want. We have far more spatial measurements than snapshots, so we're very data poor. And finally, there's enough states, so roughly here 400,000, that we really don't want to form A explicitly. We could, but it would be a huge computational cost and wouldn't buy us much in this particular problem. Okay, so in everything that follows, there's going to be kind of two sides to each of these slides. On the left is really what we're trying to do. So for example, the first step is this matrix A is going to act on vectors. So the first thing we need to do is take whatever our snapshots are and vectorize them. In this case, take the matrix and convert it from a matrix in nx by ny to a vector in nx times ny. On the right, there's the kind of equivalent MATLAB code. So if you gave me a cube, a tensor, with this time series data, we just call reshape and flatten it out. Okay? Okay, so the next step, once we have this matrix of data, is to split it up into two matrices, which we call x and y. The main idea is that x and y are related by this matrix A that we're trying to discover. So each column of X is a snapshot, and each column of Y is the next snapshot in the sequence. So you see W1 here, W2 here, W2 here, W3 here. Basically, Y should be A times X. And the MATLAB code is just, all right, in X you put everything but the last snapshot, and in Y you put everything but the first. Okay, so once we have this X and Y, we need to reduce state space because, again, we're assuming that we have way more states than snapshots, so this matrix is going to be low rank. So what do? Well, we're going to project onto the POD modes by computing the SVD of X and computing X tilde and Y tilde, which are basically the POD mode coefficients of the data in X and Y. And what we do in practice is we just compute the economy SVD, and we kind of defer this projection step to later because it's nothing that we need for the final computation. Okay, so once we're in this reduced space, the next step is to figure out what the dynamics are. And this is where DMD takes dynamics into account. The basic idea is we want to find a matrix A tilde that minimizes the error, the one-step error, in predicting Y tilde from X tilde. So we want to solve this optimization problem here. Now, you could change a loss function, something more robust from noise. You could add regularization terms to help capture properties you know this matrix should have. The reason I think that this was used initially is that it's easy to solve, right? I mean, we have an analytical solution, which is basically A tilde is Y tilde X tilde pseudo-inverse, or in terms of the SVD of X, the inner product of U and Y multiplied by V sigma inverse. So you could pick other loss functions. There's some beneficial properties to that, but the computational cost typically goes up. And in MATLAB, we don't even bother writing this. We just jump right to the solution. And this is the kind of code here where this diag term here is computing sigma inverse. Once we have A tilde, now we want to get at the DMD modes and eigenvalues. So what we do is we decompose A tilde to get eigenvectors and eigenvalues, V tilde and lambda tilde. And then it turns out that the DMD mode is just U times that eigenvector, and the eigenvalue remains unchanged. And in MATLAB, again, you call eig to decompose A tilde. It's small enough that this is typically computationally feasible. Multiply by U to get the DMD modes. And in this line here, we're getting those alphas, those DMD coefficients. And we're computing the pseudo-inverse of the DMD modes. The reason we do that is that unlike POD modes, these aren't orthonormal. They're not even orthogonal. So if you want these coefficients, you need to solve a linear system. You can't just take an inner product. So that's something to keep in mind. Okay, so that's the basic approach. Now I'm going to hand it back to Mazi, who will tell you how to apply this to an actual problem.
Thank you, Matt. So we just had this synopsis of the algorithm. We'll just summarize it over here. So again, what we're interested in doing is applying DMD to the snapshots from the cylinder flow. Okay, so what we do, we take frame by frame and create these matrices X and Y of these pairs of snapshots. One's unshifted, one's shifted in time. We compute an economy SVD of X, and we use the SVD of X to then construct A tilde in conjunction with the Y matrix here. Okay, so once we have the A tilde, then all that's left is to take the eigen decomposition of that. So then we get DMD eigenvalues, and from the eigenvectors of A tilde, we can reconstruct the DMD modes, and we can also get the DMD amplitudes. Okay, so what does that all mean? Well, let's start with looking at the DMD eigenvalues. Okay, as we said, this is related to the temporal content of the dynamics, so the temporal character of that. But before we get into how that is, what I would like to point out is just by looking at this, we see that most of these are concentrated around a unit circle, okay, so on this circle. But otherwise, it's maybe a little bit hard to interpret if we just look at all these dots around this circle. So one thing that we typically do when we look at the eigenvalues is we also encode some information about the amplitude. So that's what I'm going to show here. So in slightly brighter red and larger dots denote larger amplitude eigenvalues or modes, and the smaller and darker dots denote eigenvalues associated with lower amplitude modes. Okay, so now when I look at this, I'm going to look for the bright red and larger dots, and those are going to be the eigenvalues or the modes that are potentially more dominant in terms of the dynamics, at least as far as the amplitudes are concerned. Okay, now again, this is related to temporal information. All right, so I guess in Professor Colonius' talk, you saw this matrix exponential. So what we're doing here, this unit circle is associated with a discrete time eigenvalue. We can turn that into a continuous time. I'm not going to go through the details of this, but in MATLAB, what you could do is just look at the angle of each of the eigenvalues relative to the positive real axis, and that gives you information about the frequency of oscillation. Okay, so that's what this top line is doing in MATLAB. And if we plot those normalized by the amplitude here, we get frequencies. So this is in units of hertz versus amplitude. And so again, bright red denotes higher amplitude modes. And we see that we have this constant base flow or mean flow, which is associated with this big red dot right here. So that has real part 1, imaginary part 0. It's not changing in time. And then we have an oscillatory mode here, which is our fundamental frequency, just about 0.2 hertz, and higher harmonics of that. And so these are the equally spaced, I guess, angular quantities for the eigenvalues. Okay, now that's the frequency content. We can also look at growth and decay rates. So growth and decay rates, rather than being associated with the relative angle from the positive real axis, associated with the radial distance from the origin, from the center of this circle. Okay, so if the magnitude of an eigenvalue is larger than 1, it is growing, it is unstable. If the magnitude is less than 1, it is decaying, and if it is equal to 1, then it's a purely oscillatory mode, or it's not growing or decaying in time. Okay, so we plot those here. So growth rate in units of per second. Okay, and so this is how you get your growth rates. You just take the log of the absolute value of your DMD eigenvalues divided by the time increment, dt, which is the time increment between snapshots, right, their sampling rate. And I'm plotting those now. So growth rate, again, normalized by amplitude. And we see all of our dominant modes are essentially at 0 growth or decay rate, at least for this flow, which is expected. It's just a persistent wake flow. But we also see that there's a good series of decaying modes, and in fact there's also some, if you look close enough, if you zoom into this, there are some that look like they're actually growing. And so things like this do happen when you apply DMD. This is probably not physical over here. This is probably just a numerical artifact of the simulation to some extent. So this is something you want to be aware of when you try to make interpretations of what you're getting out of DMD. Okay, but this is basically a synopsis of the temporal content. Okay, so that tells us about time. But we also care about space because of the spatiotemporal set of dynamics. So let's look at first the question of what kinds of spatial structures or shapes can I expect to see in the domain. So when I replay that video, one way of trying to look at, before I actually recreate the video of the modal dynamics, to get a feel for what shapes I can see associated with those dynamics, I'm going to just plot the real and imaginary parts of the DMD modes. And so these are eigenvectors. In general, they're complex, so they have a real and imaginary part. And so here is the first dominant mode, which was a real eigenvalue, so it only has a real part associated with its eigenvector, this DMD mode. But the other three, so this is our fundamental frequency, and then the two higher harmonics above that. And we see that there are these structures. So keep these shapes in mind. They're going to come up again when we look at the videos. But before we do that, I want to show maybe less conventional way of looking at the mode. So when you look at the DMD literature, usually you see plots like this, real and imaginary parts of the modes. But one thing that is also useful to look at, so remember, these are complex vectors, right? So you can, instead of looking at real and imaginary part, you can also look at magnitude and phase. And this actually has a lot of nice information in it as well when you want to get some information or some insight out of what you're looking at. So if we look at magnitude, this is in some sense saying what are the most important regions of space with respect to that mode. Okay, so what are the active regions in terms of that mode? Okay, so that's what magnitude is telling us. And if we look at phase, phase tells us about leads and lags of different parts of space with respect to one another. Okay, and so what's really nice about doing this, so from this first, from the mean mode, it's immediately obvious, to me at least, that there's an asymmetry here, up-down, right? So that first constant mode captures the asymmetry of that 2s wake that we were looking at, all right? And then the follow-on modes, the next two that we look at are top-down symmetric. However, we see that there's leads and lags horizontally in the streamwise direction, right? And then we get another asymmetric top-down mode and other leads and lags in the system. So this magnitude phase picture of things actually lets us analyze things maybe in a little bit more depth than just looking at the spatial structures in terms of real and imaginary part. Okay, but this is, we've separated time, we've separated space, and we kind of threw an amplitude there somewhere. But really, you have to look at these three things collectively, okay? So really, the modes are videos. They're not pictures, they're videos, all right? They're dynamics. The modes have dynamics. So in order to reconstruct, I want to remember we started with the bull. So this is our cartoon of the flow now. We're coming up with the essence of this 2S wake. If I can reconstruct it with just these two modes. So I have my constant mode plus the fundamental frequency, the mode associated with that. If I do that, this is my cartoon of a 2S wake right here. And we see I capture the top-down asymmetry. I also capture a lot of the concentrations of vorticity that are just emanating down. Okay, but I can also refine that picture by adding more and more modes. Okay, so these are, I'm adding these sequentially based on in order of max amplitude. Okay, and so by the time we add about 15 total modes, this looks like a pretty good representation of the original 2S wake that we had. Okay, and to give you an idea of how good, so this top video here is the original snapshot sequence that we had. Okay, so that was the original data set. And then I'm using 3 modes, 7 modes, 15, 30, and then all of the modes that I had in that computation. And you see that by about 15 or 30 modes, these are pretty close to one another. And certainly these two are indistinguishable from each other and also from the original snapshot sequence. So this gives us a way of reconstructing that whole video with just a much smaller set of modes. And so we've reduced the dimensionality here quite a bit. Okay, so everything that we went through so far was basically vanilla DMD. Okay, so it was plain and simple as DMD can get, and we glossed over a lot of the other issues. So I'm going to try to summarize some of those other issues in this slide here, and some of the questions that are ongoing, but also some that have been addressed to some extent in the literature. Okay, and so one of the questions is, so I was showing you the reconstructions of those videos based on the modal dynamics, and I said I've chosen to reconstruct them based on those amplitudes. But that's not necessarily the best way to do it. Okay, and so there's been some question of how do you choose which modes to keep? Which modes do you retain when you want to do that reconstruction? So you can look at this paper here on sparsity promoting DMD. They address this question. There's another question is, well, I have all these snapshots, I ran my experiments, I did my numerical simulations, but they don't fit in memory. I can't actually do this without parallel computing or something of that sort. So if you have that issue, you can look at streaming DMD, and potentially you can do these computations on your laptop. What if you had multiple realizations? So you went to the lab, you ran many experiments, and you want to analyze all of that data together. In order to do that, so you have multiple time series, you want to use exact DMD. So this is a formalism that allows you to, rather than working with just a single time series, you can work with just, in general, snapshot pairs. Okay, what if your data are noisy? So you measured your snapshots on a physical system, you have sensor noise. How does noise, first off, affect the analysis? And how can you accommodate for the fact that that noise was there? Perhaps you didn't want it there. So you can look at total least squares DMD, and that's one way of getting around those issues. You have multiple time scales. Maybe you're not picking them all out based on the original DMD analysis that you have, but you know there's other time scales. How can you go about trying to get at those? You can look at this multi-resolution DMD. What if a linear map's not enough? Okay, and this is actually getting a little bit at this the Koopman operator aspect of things which we haven't discussed at all. But one thing that you could do is look at extended DMD, and this is actually a really nice connection with that Koopman operator business that's going on around, right? And I guess the last bit here is typically we're looking at actuated data sets. So to get that cylinder flow, we were forcing the system, okay? And we might have put in a waveform as a forcing on that, and we haven't addressed how do you deal with forcing when you look at these modes. So one way to get around that is to look at this DMD with inputs. Okay, and so that's kind of a summary of maybe the latest and greatest in DMD. And I'm going to leave this up here. So these are some key references. So these two papers were the first to introduce, kind of put DMD out there in the fluids community. And this third one here is just that reformulation, exact DMD. It's actually a nice review paper as well. So if you're getting started, I do recommend this paper here. There's some software packages available and addresses of where you can get those at if you're interested in playing around with these tools. And then some additional references based on those last set of ideas that we were talking about. And with that, thank you for your attention. We're happy to take any questions that you guys might have.